this video, we'll show more examples that use Thevenins and Nortons theorem. In this example, we're required to get equivalent Thevenins equivalent across terminals A and B. To get VTH, we need to know the open circuit voltage across A and B. So the voltage VOC. So what we could do is perform a KVL around this loop that involves VOC. Now, take note that in order to do that, we need to know the current here that flows through the 4 ohms. Now, notice that there's a current here that is 1.5 by X, and since it's an open circuit, that current will simply flow in this direction. So this is also 1.5 IX. Okay. This is the positive here. This is the negative. This is the positive here. This is the negative, based on the direction of the current. Now we can write our KVL around the loop. So this is our KVL. So we start here. So this is minus negative J3IX minus, so we go around clockwise. So minus 4 ohms times the current, which is 1.5 by X, plus VOC, okay, equals 0. And then solving for VOC, we get this one. So VOC depends on I sub X. So to solve for I sub X, notice that we can perform a KCL on this node here. So current entering is 2. This is 2 here, minus leaving, which is I sub X. So 2 minus I sub X, plus entering. So this is 1.5 I sub X equals 0. Solving for I sub X, we get this value. Therefore, we can solve for VOC. And that should give us this value. And therefore, we have VTH. To get ZTH, we apply the rules for getting the ZTH, and that would require us to disable this source because this is an independent source. We leave the source behind because this is a dependent source, and therefore that should give us the simplified circuit. And then we try to determine what is the impedance between terminals AB. So we could apply either of the 3 cases in getting ZTH. Now, for the first case, that would require us to simplify the impedances. Like, for example, 4 ohms and minus J3 are in series, we could add them together. However, because this is not a passive element, we could not combine it to a passive element. This is a source, a dependent source at that. We could not combine it to a passive element, and therefore we could not use case 1 here. Now for case 2, well, we could apply a source, voltage source, for example. But again, we might get into trouble because take note that our initial reaction would be that before applying this source, we know that the current that flows here is 1.5 by X, and that current will simply flow in this direction because this is already an open circuit here. But the problem states that the current here is I sub X, so therefore we run into trouble because we don't know what is really the current that flows here. Now, is it IX or is it 1.5 IX? To be sure about how to get ZTH, we could use case 3. Using case 3 would require us to get the short circuit current ISC. So doing that, take note that ISC is equals to 1.5 Ix. So we know that this current will simply flow in the short circuit plus the current that is in here, which is 2 minus Ix. Okay, so this current here is 2 minus Ix. Okay, so if we apply KCL here, we will get 2 minus I sub x flowing through the 4 ohms. So we get this result. So I sub SC depends on I sub x. So we need to know what is I sub x. So we can compute for I sub x by observing that we can apply KCL around this loop or KVL around this loop. So doing that, so starting here, for example, so the voltage here is, this is the plus, this is the minus. Here, this is the plus, this is the minus. So that would be minus because of this, minus J3Ix plus, so plus 4 times the current 2 minus Ix equals to 0. Solving for I sub x, we get this value. We apply that here, we get I sub SC, and therefore I sub n. Then we can proceed to get CTH. So we already know VTH. We divide that by I sub n. We get CTH here. And therefore, this is now our Thevenins equivalent circuit. For our last example, we're asked to determine this current using Thevenins and Nortons theorems. So let's first solve this using Thevenins equivalent. So in using Thevenins, we need to decide which part of the circuit we need to uh, consider as our linear circuit and transform it into our Thevenins equivalent. Well, we could use this. We could convert this part of the circuit into its Thevenins equivalent. So that part. So therefore, first we detach the circuit that involves the part where the current flows, where I sub naught flows. So we detach that and we determine the open circuit voltage across the open terminals. And let's use here mesh analysis. So we assume mesh current I sub 1 here and mesh current I sub 2. Then we plot let's plot the polarity due to the loop currents. So for the 8 ohms, there are two voltage drop. So the voltage drop due to I sub 1 and the other one due to I sub 2. For 1 minus J3, 4, and J2, there's only one voltage drop. So we proceed to write the mesh equations for a loop involving I sub 1. We notice that I sub 1 immediately becomes the negative of this current source because uh, um, the current here is already for angle negative 90 amperes. Um, We also perform a mesh or write a KVL equation here on loop involving I sub 2, and that is this equation. So 4 plus 8 plus 1, that's 13, minus J3 plus J2, that is minus J I sub 2, plus the voltage drop on the 8 ohms due to I sub 1, that is minus 8 I sub 1 equals 0. And that should give us I sub 2 equals this value. To solve V sub OC, we could then proceed to write a KVL equation around this loop. So doing that, or not on that loop, uh, on this loop. So choosing not to uh, pass by a current source. So starting here, we got negative 20 plus 8I1 due to I1, the voltage drop, minus voltage drop due to I sub 2. So that is across 8, 1 ohms and minus J3. So this is the drop here. Then plus VOC equals 0. Then solving for VOC, we get this result, which is our VTH. To solve for ZTH, we can apply case 1 because all sources are independent sources. So we get the circuit, and notice that this part of the circuit is in parallel with this one. So we can solve for that immediately. So we get this value for ZTH. And therefore we have this uh, Thevenins equivalent for that part of the circuit. And then after getting the Thevenins equivalent, we could connect back the circuit that we have detached. And this is simply a single loop. We can apply here a simple KVL equation to compute for I sub naught, and that equation should be this one, which is a sort of an Ohm's law, actually. Now let's solve the problem using Nortons. So in Nortons, we need to get I sub n and C sub n. Well, we already know C sub n, which is equals to C sub th. So let's get I sub sc here. So we apply a short circuit after detaching the part of the circuit involving I sub naught. So we apply a short circuit and determine I sub sc. Now notice that uh, this part here is actually a single node, and this fits uh, with using the method or the nodal analysis method. So we use nodal here to determine I sub sc. So assuming that this node here is V, then we label the branch current. So let's say this is I sub 2 here, this is I sub 1, this is I sub 3. Then, so this is our ground. Then we apply KCL at node V. So current entering I sub 2 equals, that is equals to 20 minus V divided by 8 plus this current, which is also equals to minus J4. So 4 angle negative 90 is minus J4 minus I sub 3, which is leaving. So that should also be V. So this is V minus 0 here. So this part here is a 0. So that is simply V divided by 1 minus J3 equals 0. In solving for V, we get this voltage. Now we can solve for ISC, which is also our I sub n, and we notice that ISC is simply this current plus the current here, which is I sub 1. Okay, so I sub 1 is 20 minus 0 divided by this impedance, so this is it. And I sub 3 is this voltage minus 0 divided by 1 minus J3, which is this one. And we get this I sub n. For peace of mind, we can check whether I sub n is correct by using the equations in case 3, which states that VTH can also be found by multiplying I sub n with VTH, which we will get to be 27.32, which is the same as the VTH that we found earlier. Thank you.